Assalamualaikum warahmatullahi wabarakatuh and very good day. So this is the topic 1, AC power, under subtopic AC power conservation and power factor correction. So the outcome of this lesson, we have 3. The first one, the student is able to understand the concept of conservation of power, determine the power factor of the AC system, and lastly, the student can capable to analyze power factor correction problems. So the principle of conservation of power can be applied both for AC and DC circuit. So in general, the conservation of power meaning that every power that generated inside a circuit is actually equal to the power absorbed by the load. So in AC power, as can be shown in this circuit here, where S is your complex power for each element. So the complex power that generated by the source is equal to the summation of all the complex power of all the elements here, such as like this equation. So for element number 1, it has its own real power and reactive power. And for the second element also, it has its own real power and reactive power. And the same thing goes to the element number 3. So since this is the real part and imaginary part, so it cannot be summed all together. So it need to be summed with the real part and summation on the imaginary part. So the P total is actually equal to P1 plus P2 and plus P3. And this P total is actually equal to the real power generated by the source. As similar to the reactive power, Q1 plus Q2 plus Q3 must equal to the Q total. And the Q total is actually equal to the reactive power that generated by the voltage source. So these equations, are they applied for series connection, parallel connection, or parallel series connection of a circuit? So let's look at how we can actually prove this. So we look at the parallel circuit first. We know that we have a voltage source here and we have two elements act as the load Z1 and Z2, and we have the current that will divide into I1 and I2. So the complex power for the source can be computed by using this formula, the voltage source itself multiplied with the current source conjugate. And from the current divider rules, okay, we can say that the current source is actually equal to I1 plus I2. Okay, and then so we can actually expand this equation, the first equation here, to from I equal to I1 plus I2. And we expand later, we will see that we have two terms here. So this is the V multiplied with I1 conjugate, which is referring to the complex power of the load number 1. And we have another one, which is VI2 conjugate, which refer to the complex numbers of the load number 2. So S source is equal to S1 plus S2. So as you can see, the equation is similar to the first equation here. So meaning that the parallel connection can use this conservation of AC power equation. Let's look on the series circuit. So the series circuit as shown here, we have a voltage source and we have two elements as the load Z1 and Z2. And based on the KVL, we know that the voltage source must equal to the voltage drop, V1 plus V2. And we know that the complex power for the source can be computed by using the voltage source itself, the value, multiplied with the current source conjugate. And we have already derived that this voltage is actually equal to V1 plus V2. So we expand this equation. So to have V1 plus V2, multiply with the I conjugate, and later when we expand again, we will see that we have the two term here. V1 multiply with I conjugate plus V1 multiply with I conjugate, which refer to the complex numbers of Z1. And the second one is actually V2 multiplied with I2 I conjugate, which is actually referring to the complex power of the element 2. So we have the S source is equal to S1 plus S2, which is equal to the equation of the general power conservation like this. So in conclusion, what we can say that whether the loads are connected in series, parallel, or in general, anything, series parallel connection combination of that, the total power supplied by the source must equal to the power absorbed by the load. So that is the conclusion that we can make. But please do not be confused on the apparent power. Okay, the apparent power is not, the total apparent power is not equal to the summation of apparent power for all elements. So that is not true. The only true about the conservation of power is that the summation of complex power is equal to the complex power supplied by the source. So this is example 4. So we will continue with the example 4.